before the class starts, there is my usual things to do. So because I'm the Utah X-ray student branch advisor, so I will promote my student branch again. So I share the recruitment drive even though it's over. So if you're still keen to join, then you can contact the person below. Okay. So because for some of you may want to be active in this core curriculum activities. So the AGM for this student branch will be held on next Wednesday, if not mistaken, right? So they are doing it using the, if not mistaken, is Microsoft Teams, right? Because now we still cannot, the government allowed to have a physical meeting, but with the social distancing and all this hygiene control, that is not easy to manage. So we'll still go for online, including all the meeting in Utah now is online meeting. Okay, there is one of classmate looking for assignment group. So if anyone who can still take in one member can contact him. He already put his contact in the chat room there. Okay, so we will continue our lecture, but before we continue our lecture, just to remind you that our midterm test will be on 3rd August, which is less than a month from now, right? So it basically covers the first 2 course outcome, right? So you can look at the course syllabus, what is the course outcome, okay? So we will move to our lectures today, continue our velocity analysis on the last example, then we will go into the accelerations. Okay, so we will look at the, because on Monday we finished this. As I mentioned that what you may have to do is to remember all the you can actually utilize these formulas here. Okay. This is for 4-bar linkage. Okay. Just a second, I'm checking. Okay, so you can see, so everyone can see my slide, no issue. So you can we can actually use the formulas here, right? So and also this is to find omega 1 and omega 2, okay? Sorry, omega 3 and omega 4, what happened to me today? Okay, so because after we find the omega 3 and 4, so then we can actually easily find the velocity of what we interested, right? Again, I always mention VA or can always be found from from the information given, because normally omega 2 theta 2 is given. So A, B, C, and D, this is the length. It's also most of the time is given, so you can find it. Okay, so this is given. So omega 2 theta 2 normally, okay, normally is also normally given, right, in the questions. So we have to find the omega 3, omega 4, theta 3, theta 4 we find from the position analysis, right? So omega 3, omega 4 we find from here in order to find this value. Because once we have omega 3, then we can find the we can actually find the velocity at the link tree at any point on the link tree. Okay. So we look at another example here. We have we will do the velocity analysis for the 4-bar linkage with vector loop method. So given a formula, we given a 4-bar linkage with the link length L1. So remember L1 is not A, because link 1 is considered the ground link, so you use D instead of A. So and then L2, L3, L4, and theta 2, omega 2. So this is, as you can see, A, B, C, D, theta 2, omega 2 is normally given. But normally before you do this velocity analysis, you have to solve the position analysis first. Analysis, right? In order to find theta 3, theta 4. Okay. So here, because this is velocity analysis, so you will assume you will automatically find this. So he just mentioned you have to find the omega 3, omega 4, VA, VBA, and VB. So this is the diagram given. Okay, so the angle, right, theta 2. So in reality, if you plug in all the value over here, your diagram doesn't look exactly like this. So you can imagine that this theta 2 now is only 40 degrees. So by right, it's only less than halfway here. 40 degrees. Okay. So that's why when I have this 4-bar linkage, actually I can easily ask 360 questions. Because every angle will have a unique set of answers. Okay. So that's why for the same diagram, I can straight away ask 360 questions. So I mean each angle one question. Then also each angle is one answer for all this omega 3, omega 4, and so on. Okay. So that's why normally the diagram is just for presentation of where the parameter is. For example, where is the D, where is the A, and so on. Right? So in reality, it may look like this. And we look at the link length. So we have B is longer than D. Okay, and then L is, so it could be something like this. Okay, in the actual one. Okay. So you can draw it with a ruler, so you can see better. So in this case, we can find. We know that the VA will be here. Alright. So again, we know that the link 2, right? Link 2. Sorry. The link 2 is over here. So if I draw a vertical and the horizontal line, so I will get this 40 degrees. So the distance here, this 90 degrees, then we will get the A. So what does it mean here is this is also 40, right, in order to get the VA. Okay. So I can draw this VA. And then VB, that's why you have to know what is theta 4 first. So then you can draw your VB component here. Okay. So this one is if you want to use the graphical method. If not, then you can just simply sketch like this. Okay. Just to build up the equation so that I can, when I look at here, I know that my equation, I can write the vector equation is VB equal to VA plus VBA. So means from here to this point is VB. I can also go the other path from here to here. Right? So that's how we build up these vectors. So that's why if you look back to the, I think this question is asked previously, or you can also refer to the textbook. So or you can try, right? If you don't know, then you try is better. So you know that you try to find whether you can get the theta 3 is 20 degrees, theta 4 is 57 degrees. So this is using the position analysis. Okay. So after we have theta 3 and theta 4, as I mentioned just now, the two equations, so you can plug in the value, right? Then you will find out that there is omega 3 is negative 4.121 and omega 4 is 6.998. So then we can use the angular velocity to find the linear velocity of point A and point B. So you can try to do that. So if those who, after you try, you cannot get it, you can always ask me. Recently, I got a lot of, that's why now I found that actually sometimes online teaching and learning, student is more there to ask questions, right, compared to the physical class. So I think average every day I get about 8 to 10 students asking me questions. Okay. So there is another one just now. The one is 4-bar linkage. So what happened to 4-bar sliders? Right. So again we have A, B, C. Okay, and also the D now is actually a moving component. Right. So we already discussed this. D has a formula that can be built from the other two linkage parameter, the A and B. We can calculate the D from the A and B with their angles. Then theta 2 here it gives 60 degrees. So omega 2 is minus 30 radian per second. That's why it's clockwise here, right? Because if I draw this clockwise arrow here, my omega 2, I will remove my negative when you try to write it. Okay, then I can find my omega 3 and the linear velocity of point A and B for this open circuit. So it will look like this. This one is called open circuit. Right. So what happens if we say cross circuit? So what it means here is you just extend this line. Then it should look like this, the diagram. So the blue color one will call it the cross circuit. Okay, it will go this way. Okay. So this one is in the position analysis. We can write out the position analysis for this 4-bar slider linkage in this way. Okay. Then if we differentiate it 2 times, so basically differentiate the one time only. So we convert this to the AEJ theta format. Then we differentiate it with respect to time in order to get the velocity function. So instead of we write it this way, we can also put it on this. Okay. Anyone has questions? No, because I heard some sound coming. Okay, so no, I assume no question yet. So this is the formulas we will get. So if we draw it in the diagram, it will look like this: VA, VB, and VBA. So it's the same thing. So then we can break it into 2 components here. Sorry. Mean we use the Euler equation again to break into the cos and sine component. Then we can break it into x and y component again. So we have two formulas, right? So again, now there is no theta 3, sorry, there is no omega 4, right? There is only omega 3 for 4-bar slider, right? 4-bar slider linkage. So we don't have omega 4, we don't have omega 4. We only have this omega 3. Then based on the omega 3, we can calculate our velocity here, okay? So again, just now the d. Okay, you can calculate the d directly based on these formulas. Okay, so that is velocity analysis. So there is actually a much more questions and example in the textbook, right? So you can try to read from there, right? Then we'll move on to the accelerations, right? So again, we can use graphical method. We can use analytical solutions for this acceleration analysis. So acceleration is defined as the rate of change of the velocity with respect to time. So means we will differentiate the velocity with respect to time in order to get the acceleration. So for linear motion or translation motion, so it's dv over dt. For rotational motion is d omega over dt. That's where we get the alpha, which is angular accelerations. So again, if we now start by looking at the link 2, right, which only do the pure rotation, we call it, right, pure rotation. So
sir, we can't see the slide.
Hey, sorry. Then thank you very much for informing me. I forgot to share the slide. Thank you. And I can repeat now. Okay. So for we will be in this acceleration analysis. So again, we can use graphical method and the analytical method. So as I mentioned just now, the acceleration is defined as the rate of change of velocity with respect to time. So this one is for translation motion. Okay, this is for rotational motion. Okay, so for rotational one, so we will get angular acceleration. This one will get accelerations. So again, we will first look at the link 2. Okay, so this is a pure rotation. So we can specify the position of this point P as RPA, or we can write it in terms of PEJ theta. This is how we write it in the different form, okay? Different format. Okay? So by differentiate this with respect to time, we'll get velocity. Right? So if we differentiate again, then we will get the acceleration. Right? But I think in the dynamic fundamental, the revision that we done, so you will notice that when for rotational component, when we differentiate the velocity with respect to time to get the acceleration, then our acceleration will have two components, right? So we will have a tangential component and a normal component, right? So what it means here is now the accelerations will be here, for example, because this is where when my omega 2 is going this direction, okay, when my omega 2 going this direction, my alpha 2 is opposite the motion of omega 2, which actually in this case consider the accelerations of the system. So my VP will follow, okay, they follow the omega 2, right? So then the AP normally will kind of relate because the direction is not exactly follow. So it's actually related to the angular acceleration. So in this case, because the angular acceleration is opposite direction of the angular velocity, so it's actually a deceleration. It's not moving the other side. So uh, some of you or even myself sometimes will confuse when we say negative acceleration. Right? Negative acceleration doesn't mean you go the other direction. Right? Just like your car, when you step on the pedal, you are accelerating the car, so your accelerations will be same direction as your uh, velocity direction or your movement direction. But then you step the brake, then you get the negative acceleration. So your when you draw in the diagram, your acceleration will be opposite your motion. Right? So that is the deceleration. So you find out that the acceleration will actually be in a certain angle. Okay? So that's why we can always break it into the tangential component, which is here, and also the normal component. Right? Right? Because later when we do the dynamic analysis of the linkage, we need this acceleration because we are using the Newton's second law, which is the summation of force equal to ma. Yeah? So that is where we need the acceleration. Right? So we move on. So if in the case that when the reference point A here, right, has its acceleration also AA, so then my acceleration at point P will have to be AA plus APA. So mean this one plus this one. So if you look at the diagram, because I know my A straight away is like this, right? So normally when we do draw this diagram, we will refer to the tangential and the normal component, because at least this one and this one we will know its angle, okay? Because here, for example, this one now is theta. So if I draw like this, then I will know that this is also, where is the theta? This is theta, okay? And this is also theta over here. So you have, that's why I say when you try to solve this, your trigo knowledge have to polish up. So you have to know how to see the where is the theta, right? This angle and this angle, last time if you study in mathematics, they will say this one and this one is the same. Alright. So when this is the same, so if I cross another line and cross this line, which is 90, so then this one is also the same. So this is trigonometry. So you have to see it slowly. So from here, then I will know where is my APT, the AP tangential and AP normal. So that's why once I draw my AA, if this is given, okay, I know it's horizontal and its magnitude. Okay, so actually from here up to you, you can draw the APN first, or even you can draw the APT first. So in this case, you draw the APT first using the angle. So it should be 90 plus your theta. So you can draw it that way. Then you set a 90 degree, you draw your APN. Right? So the question now is we may not know where you want to draw this line. Okay? So that's why we will continue to do the calculation here. Right? Next. Okay. So now we will move on to find all the information here. So that's why for analysis, acceleration analysis, so you must do the position analysis first. That's why it's very long questions if this is being asked. So normally when I only want to test you on this acceleration analysis, so I will also give you all these parameters. Okay. But if I want you to do all the three analyses, the position, velocity, and acceleration analysis, then you can see how many parameters you have to find. This is all. This is a lot. This one will be given. Okay, this one will be given. This one will be given. But basically, the rest of it you have to find. Okay. Okay. Because we have to do step by step, settle the position analysis to find these two values. Then velocity to find these two values. Right? Then only we can do acceleration to find this value. Right? So this is using the position analysis, velocity analysis, and acceleration analysis. So that's why if you say this question now asking about acceleration, so it will give you everything from here. Then you only find this. Okay. So again, we look at the diagram. It's a 4-bar linkage. Okay. So now you will see that they give us the alpha 2. Right? They give us alpha 2, omega 2, theta 3, theta 4, theta 2. All the link length is to be given. Okay? So then we can start to do our calculation. Before we continue, so similar thing, because now acceleration is this direction. That's why you will see your A transpose is here. A normal again will be point to the reference rotation point, right? So now if we look at the ABA, means the A here will be the reference. Okay. So the thing is now your ABA tangential, and ABA tangential, it could be this direction or even here, depending on your, I can't see, you're using yellow. Depending on your alpha 3, okay, where it go up or down. So it depending on the alpha 3. But BA normal will be here, right? Then for the link 4, so again AB normal will be here. Okay, AB normal will be here. So again, now by AB tangential, it could be there or even this side. Then it depends on this alpha 4. Okay. So the vector polygon, so what we can do? Okay, so we will start with the AA, right? Because AA is the one known when we know the alpha 2 and omega 2. Maybe we have a look at here. So if you look carefully here, your A tangential is the radius multiplied with the alpha. Your A normal is the radius multiplied with omega square. Okay. That's why over here, this will be your link 2. So what symbols we use? I will say RA. RA multiplied with alpha 2. This will be RA multiplied with omega 2 square. So this is how you can calculate the value of it. So we can start from here, right, this point. Then we draw this one. As long as we know theta 2, okay. As long as we know theta 2, then we can draw this. And also 90 degree. Then we draw this. So these two lines is known. Okay. So you can also find a resultant acceleration, which is connecting this one But basically, sometimes this can be nervous, right? To reduce the number of lines in the diagram. Okay? Then the ABA normal will follow this line, okay? This line here, the AB line here. So I can measure, right? So how we measure? So this is, anyone know what is this angle? This is theta 3, yeah? Because the angle is here. So if I draw another horizontal line here, this is theta 3, yeah? So again, it's like that. When this is theta 3, this side is theta 3, yeah? That's why I can get a theta 3 and draw it downward, right? You just draw it long, right? Because we don't know where is it, right? Then on the other side, we can draw the AB tangential, because when we know the theta 4, so I can know the AB tangential will be on PP line here. So just draw a line, right? Alright, so from here then we will have to calculate, right? Do some calculation here. That's why later when we have AB normal, this diagram we will draw it slightly different. Actually, this line, you can also start with here, 90 degree. Then only you move this line over here. Depend on what this is 90, right? And right, this will be AB normal, ABA tangential, right? So you can build the polygon depending on, you can just combine all the acceleration component together. So here after the ABA normal, he connect to the AB normal, right? So you can also do ABA normal, then connect to the ABA tangential, then only you do this. So you have 90 here and 90 here. If not, you will check with this line. Maybe I change another color here. If not, you check this line, this is 90, right? You check with this line, that is 90 here. So they are perpendicular, because this is tangential component, this is normal. This is tangential component, this is his normal component. They are one pair, okay? So there's other alternative way to construct it, okay? So it depends on which one you draw first. So for example, this one, you start with the AA normal, then AA tangential, okay? Then connect to the ABA normal, ABA tangential. So on the other side, you connect the the AB normal, and then to the AB tangential. So this is 90 because they are one pair. This is 90, there are another pair here. This is 90 degree again, there's another pair. Okay, so this is you can see that there is if the alpha 2 is 0, so just now I already say that the AA tangential is R2 alpha 2, AA normal is R2 omega 2 square. So when alpha 2 is 0, means this component will be 0. Right? So you just remove the AA tangential. Okay? So now if we start from O, I have AA normal, then I don't have AA tangential, so I can straight away go to AA normal, which is same as here. And then here is ABN, right? AB normal. So 90 degree, I will get AB tangential. So this one ABA normal here. At the end here, I put 90 degree. That's where I will get ABA tangential, right? So then we will find the meeting point of this. And then now, because just now is all finding the the acceleration is all, at all these points. Okay, so for sure O2 and O4 there is a fixed ground, so there will be no value. So we can only find the AA and AB. Okay, you look at here. So basically we are finding AA, which is the A is the AB, sorry, AA tangential plus AA normal. AB is AB tangential, AB normal. Okay. So when we know the alpha 3 and omega 3, then we can actually find the acceleration at any point. For example, here we have point C here. Later, when we do dynamic analysis for the linkage, we may have to find the acceleration at its central gravity. Right? So that's why we also find it here. So don't worry if you still slightly blur during now, because we will keep doing, especially this acceleration, we will keep doing this for maybe coming another 2 to 3 weeks. We are still doing this. Right? So later, that's why then we have to know, as long as you know the distance here, right, to the reference point, the distance to the reference point, right? So then we can calculate, because once we know the distance and its angle, right, as well as this one. For example, now this is C, right? So then I will know that my AC tangential is either going here or here, which is 90 degree to the link connected to the A. So then I will have my AC normal is here, right? So now again you see that it starts from here, AA normal, AA tangential. We start with AA tangential first, then AA normal, right? So the other side, what he did is he will go with the ABA normal. Wait, why? Oh, this is not to find C yet. The next one only. So what he's trying to do, this is the same thing as what we have just now. Right? This is the graph we have just now. So we have ABA normal, ABA tangential here, AB tangential here, AB normal here. Okay. So what he wants to show you is that now I can ignore the ABA. Okay. Let me reconstruct it. So instead of we looking at ABA, so he actually looking at the AC, the point C here for the calculation. Maybe you go to the next diagram. Is it clearer here? Let me check how to make it clearer. So this, if you look at the coming one here, it only draw AA, which is actually this line. Right? So he removed these two, right? But actually when we draw, anyhow, unless you already know where is the A, you already recalculate what is the AA and its angle, so you can straight away draw this line. If not, then you still have to construct the AA tangential and AA normal here. So then what he did is then we can straight away, because this is AA, so we can join with it. This is ACA. Okay. So that's why then he can draw the ACA here. normal, which is this one. Oh, so just now the one we still can have this. A tangential, A normal. Okay. So then we continue with this ACA. Right, so that is the angle. So that's why it is important to find what is this angle. Right? So that we will get this one. Right? So the angle, if we calculate, this will be the theta. Maybe I put it theta C. Right? And then the 90 degree, we will get the AC tangential. Right? So now we will find out that there is a point and point. So we just join them. It will become my AC lah. Right? AC. Do we have any example here? No. Maybe I will look for example, then we can discuss on the example. So that is a graphical way of doing the calculation of it, right? So normally you can find this. It's not usual, because ACA normal is, for example, I call this RC. It will be RC omega 3 squared. Okay? And so say similar, go to here. Okay? ABA normal, this component is R, if this is the R3, yeah, then this is the R3 omega 3 squared. Okay? So then what else? The AB N normal is R4 omega 4 squared. Okay? So this one will be R4 alpha 4. This one is R3 alpha 3. Okay? So that's where you can calculate all the value. So this is how we calculate the alpha 3 and alpha 4. Okay? Or it's just a formula that I mentioned just now. That's why we have AB tangential is BO4 alpha 4. Or I always call it R4 alpha 4. I mean it's the link length number 4. Right? So if we look at the ABCD, so this is C alpha 4. Right? So this one, we can find the ABA tangential is BA alpha 3. Yeah? So, or we can call it AB, or we can call it B alpha 3. Right? So even though we have a vector calculation like this, but because we have normal and tangential components, so we can break it down to this. So again, you can see that the calculation involves a lot of these sine and cosine rules. That's why I shared the simple notes to you on the last week, on the Monday class. So we will still stick with the same diagram. As I say, every diagram like this, okay, with the same link length, it can be already have 360 questions. Right? So once I change the link length again, so you have another new set of questions. Okay? So everything is the same, because we don't want to change. We don't want to repeat all the position analysis, velocity analysis that we done previously. So we have the link 1 at negative 36 degree here. Then link 2 is 57. So now we find alpha 4, AA and AB. So it gives us omega 2 is 20 radian per second counterclockwise, right? Constant. Okay. So when you read question, you have to be careful. When it says angular velocity is 20 radian per second at a constant. So it means that your alpha 2 is indirectly, it already tell you alpha 2 should be 0. Right? Because when omega 2 is constant, so your acceleration is 0. Okay? And most of the questions you will find out this is the condition. Right? So far in the books, very seldom you will have alpha 2 has a value. Right? One of the reason is not simply they give you alpha 2 is 0, because in practically most of the machine is running at a constant speed. Right? The motor normally run at its optimum speed for energy efficiency problems. Right? So the diagram is still the same. So now we look at it. What we are trying to do here is, again, we find is omega 3 and omega 4 using the velocity analysis. Okay? So this VBA can be found from the velocity analysis. You can try to do it. Try. Then if you can't get it, I can discuss with you. Right? Now is much more simple. Right? We can call through the Microsoft team. Then I can also meet you. Right? So then we can VA is very straightforward. It's just R times the radius times the angular velocity of the link tool. So we get this 0.8. Right? Okay, so the things that we are interested is on the accelerations. So to find the AB, so we can take a AA plus ABA. So we can write it in normal and tangential component. Okay, so you can see that this is normal component as I mentioned. Now you see you use R4, so it can be C omega 4 square. Don't blame me. This is how the book put the symbols also. So I just we just follow the books. Okay, so it use R4 in this case, okay, which is the link length of link number 4. Right? So then omega 4, R4, alpha 4 here. So this is normal tangential. Then for this, because this one is R2 alpha 2, because now alpha 2 is 0, so it will become 0 here. So we only have R2 omega 2 square and R3 omega 3 square, R3 alpha 3 square. That is for the ABA normal and ABA tangential. So we substitute all the value. Then you find out that on these equations you will have two unknown, right, which is the alpha 3 and alpha 4. Okay. So if we draw it in the diagram, that's where I have, you can see, so because now there is no AA tangential, so we only have AA normal. Okay. So he draw it in the scale dimension 16. Okay. With the angle. So if I put the horizontal line here, this will be 57 degree. Yes. Then the ABA normal, okay, which is this one, ABA normal, or it didn't specify here. So I will try to draw here. So you have ABA normal is here, and then ABA tangential. So I just draw two directions because we do not know where you go. Okay? So at least I know this one, ABA normal, which is 2.6. Okay. Then ABN, right? AB normal. This is the direction. So I can draw this line. Yeah? So the value we calculated is 3.56, right? Then 90 degrees. So we draw this line. This is the AB tangential. So here also the same, I got this line, I set 90 degree, I draw a line. And because I put the orange line, yeah? These two orange line is something we don't know, right? But at least we know the angle is 90 to the normal component there, 90 to here. That's why after we draw, then we measure its length. It will give us this value. Then we can measure its angle. Then it will give us the angle of that ABA tangential. This one we can find out the angle. So the other one is we measure this. In order you get 12.9 here. So this is the ABT. So from here you substitute this back. This is the AB tangential. So I can find alpha 4. I take this value, I substitute here. So I can find my alpha 3, which is over here, alpha 3 and alpha 4. So you see, you take 8.5 divided by 0.96, something wrong here. And then alpha 4 is 12.9 divided by the 0.122. So we get these two values.
Sir,
yes.
Where did we get the ABA normal again, the 2.6?
Calculated this one. ABN or ABAN.
ABAN. The 2.6.
Is calculated R3 omega 3 squared. Because previously we already have. You have to find this one first. Right? So then you can calculate this 2.6. That's why, as I mentioned, you must do the position analysis to find theta 3, theta 4. Then do the velocity analysis to find omega 3, omega 4. Then only we can solve this, unless all these parameters is given in the question. If not given,
this case, the omega 3 is we just take the value from.
We take the value from the previous calculation.
Okay.
So we substitute into here. So we get this similar to this one, the AB normal. Alright. So we have R4, we have omega 4. So we can calculate this 3.56 that can put here. Right. So you can see the purple color line and this I better erase here. The purple color line is something that we calculated with the information we get from the position and velocity analysis. Then the two yellowish orange color line, that is the one we're trying to measure from this diagram. So we can find the alpha 3 and alpha 4. Okay, I think it's 1 hour now. We will stop here. So if you still have any questions, you can ask me. Okay. If I find out I cannot type and answer you, maybe we will find a time and then I call you. Right, as a similar to what we have physical meeting in before we have this COVID-19. So but before we leave, so in the chat there I also share a PDF file named symbols. Right. So there is I find out there is a very interesting document that actually introduce you all the symbols and its name. So for your information, symbols also have capital letter and small letter. Right? So you can have a look, right, into that symbols. Okay, I think I will end the class today. So I will see you on next Monday again. Thank you very much.